My name is Matthias Hutsenbelt-Buys. I'm a PhD student at the University of Antwerp. I'm going to present to you our paper on pre-trained word embeddings for goal-conditional transfer learning in reinforcement learning. This is joint work done together with Kevin Metz and Steven Latte. In reinforcement learning, an agent is tasked with solving a sequential decision-making problem by finding a policy which is capable of executing actions in an environment. This policy is conditioned on a reward and a state signal. In goal-conditional reinforcement learning, the setting of our paper, the agent is capable of executing multiple tasks by being conditioned on a goal vector. Typically, in reinforcement learning, algorithms start out tabula rasa. This means that they train a novel policy for each single new task. This, of course, leads to a very low sample efficiency, requiring a lot of interaction with the environment. In lifelong learning, the setting we consider, previous learned behavior is reused in order to solve novel tasks. Such behavior is often called a skill or a temporal abstraction. This also allows for compositionality, combining different skills in order to solve even more complex problems. We consider lifelong learning in a combination with natural language, because natural language is a very powerful abstraction for transferring knowledge. For example, if I would tell you where that you can find the microwave on top of the fridge and you know how to reach the fridge, you also know how to reach the microwave. The task we consider in this paper is the task of object navigation, finding objects in an environment. For this paper, we created a simulated domestic apartment consisting of three different rooms, and in each room there are a few objects represented by cubes. As stated, the agent receives an RGB input of a 3D rendering of the environment in its current position. Our method consists of three parts. We first train a base policy on some prior tasks. Then, when we are confronted with a new task in a lifelong learning setting, we select the most similar task, and in the final stage, we transfer the knowledge from this selected prior task to the novel task. In the first step, we train a base policy using a deep recurrent queue network, and we combine this with the goal vector. This goal vector, we have a few options we needed to consider. We could either use the entire state space, but it is a very difficult problem because it is very expressive. We could use a typically used one-hot representation. However, this does not allow to add novel goals once the agent has been trained. So we decided to use natural language to encode the goal. We took a pre-trained word embedding. Then this allows us to express the goal as a region in the state space, and it is also expandable. We're able to express novel goals that doesn't need to be specified in advance. In the second stage, when we're confronted with a novel goal in our lifelong learning setting, and for example, we already know how to find the shower and the microwave, we need to consider which of our prior goals we can use in order to learn a new task. For example, find the bathtub. We did this by testing the cosine similarity in our pre-trained word embedding space between the different prior goals and the novel goal. So in this case, bathtub. In the third part of our method, we initiate a novel policy for this novel task completely random. But we extend the epsilon greedy exploration scheme to also incorporate biased sampling. For example, the agent either takes an action greedily, or it can explore the environment by taking random actions, or we introduce an additional option, namely sampling from the closest prior goal. So we take the action as if it would be selected by the policy matching the closest goal in our word embedding space. We do this with a prior sampling rate called alpha. When we look at our preliminary results, we see that indeed, when tasked with a novel object, for example, bathtub, the goal closest in our word embedding space, namely shower, also transfers back.